For thousands of years, the night sky has ignited our imagination. We built telescopes, refined optics, and mapped the heavens. Yet, the atmosphere always stood between us and the universe, blurring the most distant galaxies, blocking ultraviolet light, and hiding the cosmos behind layers of distortion. But in 1990, humanity pushed a telescope beyond that barrier. A machine suspended in orbit, free from atmospheric turbulence, equipped with optics so precise they could detect the width of a human hair from kilometers away. This wasn't just another scientific instrument. It was the beginning of a new era. The era of the Hubble Space Telescope. A symphony of optics, avionics, engineering, and one of the greatest scientific achievements in history. The concept began in the early 1970s. A space-based observatory designed to detect light in wavelengths that Earth's atmosphere absorbs, especially ultraviolet. NASA partnered with ESA, and after nearly 2 decades of design, manufacturing, testing, mirror polishing, integration, and delays, the world's most advanced optical telescope was ready. Hubble was built with a philosophy unique for its time, designed for maintenance. NASA knew components would fail, they knew systems would degrade, and so Hubble became the first orbital observatory built to be repaired by astronauts, a decision that would save the mission years later.
Pressure water system arm. T-minus 10, 9, 8, 7, 6, 4, 3, 2, 1, and liftoff of Space Shuttle Atlantis, a final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
On April 24, 1990, the Space Shuttle Discovery carried Hubble to low Earth orbit, 547 kilometers above Earth. But soon after deployment, engineers noticed that Hubble's images were not just blurry, they were catastrophically distorted.
You would think that it would be pretty straightforward to find a focal point for a telescope, and indeed as we set out to do this, it seemed like a straightforward activity. However, as we began to get further into this, we began to realize there was no one specific focal point that was optimum. There were a series of focal points, each of which was giving us an image which was not meeting the specifications we needed, yet each of these points had a little different characteristic.
I guess the important question in light of all this is, can we do unique and important science? That's the most important question. And the answer is an emphatic yes. We can still do important and unique science. 100% of the time available to Space Telescope will be used doing important and unique science until we can solve some of these problems.
A 2.2 micron error in the curvature of its 2.4 meter primary mirror, smaller than a fraction of a red blood cell, was enough to shift incoming light and destroy image clarity. The world ridiculed NASA, but engineers saw a problem that could be solved if humanity was bold enough to try. 3 years later, the boldness paid off. In December 1993, astronauts aboard the Space Shuttle Endeavour performed a series of complex spacewalks to repair Hubble. They replaced instruments, installed COSTAR optical correction modules, upgraded gyroscopes, swapped out onboard computers, and restored Hubble's vision. These EVA operations were extremely delicate, installing replacement avionics systems while orbiting at 27,000 km per hour, with Hubble's thermal environment swinging between plus 120 degrees Celsius in sunlight and minus 100 degrees Celsius in shadow. When Hubble opened its corrected eye again, the universe appeared with unprecedented clarity. This single mission transformed Hubble from a global embarrassment into the crown jewel of astrophysics. Hubble is far more than a camera in space. It is a masterpiece of avionics engineering. Attitude Control System. Hubble's pointing precision is extraordinary, 0.007 arc seconds. That's like holding a laser steady on a coin 300 kilometers away. This stability is achieved through 3 fine guidance sensors, interferometric devices that lock onto guide stars and provide ultra-precise orientation data. Reaction wheels, adjustable momentum wheels that rotate the spacecraft without using propellant. Rate gyroscopes. 6 gyros measured angular velocity. Failures over the years required replacements during later servicing missions. The synergy of these systems allows Hubble to track distant galaxies for hours without drift. Thermal Control System. Hubble experiences dramatic thermal cycles every 90 minutes during each orbit around Earth. To maintain optical alignment and instrument stability, the thermal control system uses multi-layer insulation, radiators, electrical heaters, thermostatically controlled components. The telescope must hold its mirror geometry within nanometers, despite extreme heating and cooling. Power subsystem. Hubble relies on 2 25-foot solar arrays that generate between 2,200 to 2,800 watts. Energy is stored in nickel-hydrogen batteries designed for thousands of charge cycles. During servicing missions 3B, new rigid arrays were installed, lighter, more efficient, and reducing structural jitter to improve pointing stability. Onboard computing and data systems. Originally, Hubble used 1980s era DF-224 computers and magnetic tape drives. Over time, these were replaced with radiation-hardened 486 processors, solid-state recorders, upgraded data handling units. This modernization increased Hubble's data rate, reliability, and scientific output dramatically. Communications and telemetry. Hubble communicates with Earth through NASA's TDRSS satellite network. High-gain antennas transmit science data. Low-gain antennas handle redundancy and commands. Continuous telemetry monitors temperatures, voltage, gyros, and hundreds of critical parameters. This avionics architecture enables remote control of nearly every subsystem. Number 1. Measuring the expansion of the universe. Hubble's observation of Cepheid variable stars refined the value of the Hubble constant, narrowing the age of the universe to 13.7 billion years. Number 2. The accelerating universe. Hubble observed distance-type LA supernova, revealing that cosmic expansion is accelerating, a discovery that led to the concept of dark energy. Number 3. The Hubble Deep Field. By staring at the tiny, empty region of days, Hubble uncovered thousands of galaxies in every stage of evolution. Number 4. Stellar birth and death. Iconic images like the pillars of creation reveal the formation of stars inside thick dust clouds. Number 5. Exoplanet atmospheres. Hubble detected water vapor, sodium, and haze in the atmospheres of distant exoplanets years before James Webb Space Telescope. Hubble sees ultraviolet, visible light, and near-infrared. James Webb sees mid-infrared and far deeper cosmic structures. Together, they provide a multi-wavelength understanding of the universe's earliest stars, galaxies, and exoplanets. Hubble shows us cosmic structures with sharp visible detail. Webb peers through dust to ancient galaxies. Two different telescopes, one shared mission. Hubble is aging. Some gyroscopes are failing. Batteries are decades old, and thermal systems are weakening. NASA predicts Hubble could continue operating into the late 2030s. But without servicing missions, each year is uncertain. There is ongoing discussion about a potential mission to reboost Hubble's orbit or stabilize its systems, possibly using commercial spacecraft. But whatever the future holds, Hubble has already secured its place in history. The Hubble Space Telescope is more than a machine. It is an engineering triumph, a masterpiece of avionics, and a window into the deepest mysteries of the universe. It has revealed the birth of stars, mapped the growth of galaxies, measured the expansion of the cosmos, and transformed our understanding of reality. Hubble showed us the universe as it truly is, beautiful, vast, and full of wonder. And long after its final orbit decays, its discoveries will continue to guide the next generation of scientists, explorers, and engineers. Hubble didn't just observe the cosmos, it changed humanity, and its legacy will shine for centuries to come.